Beard's getting long. Hey yo, what's up guys? Baby Bear 4812 coming at you one more time. Today we're going to be solving problem number 723, Candy Crush, based on everybody's favorite old school phone game. I guess it's old school at this point. It's a really good problem, and it hasn't received much attention yet, it seems, from users, but Bloomberg's been asking it a lot, and so has Google a few times as well. I thought it was a really cool problem, actually, so I thought it would be worth diving into and trying out. The logic itself, I think it's appropriately tagged at a medium. It's definitely a doable problem. It does require a bit of thinking, though, and the implementation itself, I'd say, is a bit heavier, maybe uses a few extra lines of code than what we're usually doing in one of these questions. So with that said, if you haven't tried the problem yet, pause the video, try it out, come on back. But otherwise, let's just jump into it. So we're told that the question is about implementing a basic algorithm for Candy Crush. Okay, so I'll kind of skip through this and I'll explain it myself through a couple of examples, but we're given a 2D board. Okay, and at any given point at board ij, if we're given a 0, that's a blank. Okay, it's a blank cell. Anything else is fair game. It's not blank. We're told that the board represents the state of the game following a player's move. Now you need to restore the board to a stable state by crushing candies according to the following rules. So for those of you unfamiliar with the game, first off, I'd go check it out. And second of all, for those of you who are, just as a refresher, if I pop a bunch of candies and then I'll have some new ones fall, or the existing ones will fall, that might form some other combinations, which will then crush more candies, and it'll keep dropping downwards. So we need to go through all those iterations until we're done with the crushing. We're not just doing one step. We're going to do everything from our initial state until stable state. All right. The rules, more formally speaking, are as follows. If 3 or more candies of the same type are adjacent vertically or horizontally, crush them all at the same time. These positions become empty. Okay. After we crush everything simultaneously, if an empty space on the board has candies on top of it, the candies will drop until they hit a candy or the bottom at the same time. No new candies will drop out the top boundary, so we don't need to worry about new candies coming in, all right? After the steps, there may exist more candies that need to be crushed, like I said earlier, and if so, we need to repeat the steps above. If there does not exist any more candies that can be crushed, so the board is stable, return the board as it is. You need to perform the above rules until the board has become stable. Cool, they gave us some example here and they walk through it. Basically in this state in the game right over here, you see that the 1s and 2s here form kind of a non-stable state, so those will be crushed, and after that happens, we see a bunch of 5s come down, and then those will be crushed, and I'm walking through this quickly because I will give a slightly more detailed description in a second, but I think it's for the most part understandable, and we're going to do this all in place. So there are a few major steps that we're going to have to take here in understanding this problem. First off, we need to understand what it actually means to crush something. Well, we know what it means to crush something, but I want to get particular about what we're going to be doing here. If I've got a whole row of candies, that is not a row, that is like a diagonal. It's a bit better. I got a row of candies here, right? And let's say that each of these candies, each of them is represented with an integer, okay? That's how we're given in the question. Let's say all of these are 1 and then this one is a 2. Because we have 3 in a row here that are 1s, these 3 will all be crushed. We somehow need to tag these and make sure that they go bye-bye Charlie. What I want to clarify is that this, if we had an arrangement like this where this is a 1, and maybe the rest of these are, these are 3s, and this is a 4, what will be crushed is still only these 3. Because we have 3 horizontal ones adjacent, we will not be doing this L formation here. The reason we're not doing this L formation is that column-wise, we only have 2 1s, okay? We don't have 3. If we had a 1 right here, and now we had 3 1s in a column, then these would be crushed, as would all of these. So these adjacent ones, we make these kind of L shapes only if we've got a row or a column, both of which have at least 3, okay? I just wanted to clarify that because I've seen some confusion over that before, so I wanted to make sure we get that out of the way. So apart from that, let's really think about what's happening. Like, how do we determine which candies we're going to crush? First off, the solution isn't going to be particularly elegant per se because we do almost in some way need to do like a simulation and a full walkthrough of the board every time. So I don't have like a super, clever, hacky way to get through this quickly. And quite frankly, you don't need to. The solution we're going to go with is a good one. You could argue it is kind of brute force, but I believe it's the best way to do it. If you guys have a better, more optimized way to do it, let me know down below. But as I was saying, we're essentially going to do this. We're going to have 3 steps. Okay. The first step is going to be, let's actually tag elements that are adjacent to each other that have 3 or more repetitions of themselves. So what we're going to need to do is we're going to need to check rows. That's going to be one thing. So maybe our step number 1 is going to be check. I'll say check plus tag rows, and we're going to figure out how to tag these appropriately, okay? Once we do that, we've now checked our rows one by one. The second step we're going to need to do is to walk through column-wise, and then through every single column, see where we've got 3 or more items that are ready to disappear. So I'm going to write check plus tag columns. All right, columns. Now, after we've done that, we've somehow tagged these things, and again, we'll talk about exactly how we're going to identify them. But after that's said and done, then we actually got to do the dropping. Okay, so I'm just going to call that gravity. And when I first did this, or the first couple times I tried this, I thought this was the hardest step. It's going to be very similar to another very common utility problem. And I'll walk through the solution to that one, but it won't be as bad as you think. Big picture though, this is really all that it takes. Every single time we do one iteration of this, we're going to have to ask ourselves, are we in a stable state yet? Okay, so we're going to have to keep some sort of track of, are we in a stable state? The way that I know we're going to do that is we can just keep some sort of Boolean at the top of our function. And with this Boolean variable, we can say, well, if we didn't check any rows and we didn't check any columns, or tag them, excuse me, I should say, if we didn't tag them as saying there are 3 or more candies that need to be crushed, then we haven't done anything. And at that point, we're done, and we're going to return what we got, and that's our stable state. So let's actually talk about how we're going to do this tagging of the rows and then the columns. Although the logic will be the same. Let's say I'm going to make another row here. So what I'm going to do is I'm going to say, make this one a bit longer. So I'll make a whole bunch of these. What I want to say is this: 2, 1, 1, 1, 1, 5. This is what I'm going to do, okay? So I need to go through, and visually looking at this, we understand, like, okay, there are 4 1s in a row here. I'm going to need to tag these, and I want to get rid of these. So one thing that you can think about is you just say, okay, well, if I see 4 in a row, or if I see 3 in a row, let me start making these zeros. So I see these 3 in a row. I say, okay, well, this will be a 0, this will be a 0, this will be a 0. Bam, those are going to disappear. Then we get to the 4th, and it's like, wait. Or you know what, even better yet, fine. Let's say you somehow checked all 4 of these, and you said to yourself, I see 4 in a row, they're all going to be zeros. Fine, fair enough. The issue with that is, what if we had a column coming down here, and this column had a whole bunch of 1s, right? But we were first checking the rows, so it's like you couldn't check the rows and the columns all simultaneously and grab all these. So there's a bit of an issue in dealing with that. How do we actually tag these such that we preserve the, I'll call oneness, since the number 1, the oneness of this cell, so that we can compare it to other potential options as we're going both across and up and down? Well, since all these candies are going to be positive numbers, and we're told that in the question and down here in the constraints, we can simply say, if I find numbers that match in absolute value, then I'm going to tag them as being the same. What I mean by that is this: I'm going to take a slider of width 3 at a time and move it across my rows. The reason it'll be width 3 is because what I'm interested in is tagging an entire block at a time. I'm going to start by looking at these 3 units right over here. I see a 2, a 1, and a 1. These 3 numbers are not equal. Their absolute values are not equal. And the absolute value is important. You'll see why in a second. So I'm not going to do anything. I'm going to take my slider of 3 and move it over this way now. Now I'm checking these. Well, this equals this, and this equals that. So they are all the same. So these 3 are going to need to be crushed. But instead of setting them to 0, what I'm going to do is I'm going to set them to -1. I'm going to set them to -1. I'll set them to -1. The reason I'm going to do that, actually, let me do this. Let me get rid of this first. So I'm going to set the -1, -1, -1. The reason I'm going to do this is as follows. Now I'm going to take my slider and move it 1 more over. I'm going to move it 1 more over here, and I'm going to say to myself, okay, well, sure, these 2 are -1, -1, and 1, but the absolute value of them is the same, and that's going to be the key thing to understand here. If the absolute value is the same, I can then also mark this one. I want them all to be negative because I want them all to disappear. The reason this is important is because now let's pretend we go column-wise. So we had these are -1s. I got a column here now, and this happens before the crushing, remember. So we're tagging the rows, we're tagging the columns, then we're doing the crushing and the gravity. If these are 1s, I'm doing my same block of 3 comparison looking this way vertically now, I can still say to myself, okay, these will still match up, so I want to crush all these in this direction too. So these are going to be set to -1. Then I'm going to take a step down and look at these three. Again, we're in the same position. This is going to be -1. And what's going to happen is, so what I've just described here is actually our first two steps. It's both tagging our rows and tagging our columns. We're just going to switch the order of the for loops, but I mean, fundamentally, the way we're moving this window will be identical in both cases. So this explanation kind of covers the tagging, and let me know down below if you have any questions or if that doesn't make sense. What we're then going to do about the gravity is this, is imagine that we now have, I'm going to draw the rest of the board here. I'm just going to make it up, and maybe y'all don't need to see my face here, dude. There we go. Move myself out of the way. Back into the sphere. There we go. So I've got, oh, and I lost that. I've got, my rows here, and what I'm going to do is this, is I'm going to say, I'll put in a bunch of random numbers. These will be, I don't know, 7, 3, 4, 5. I'm filling in random things here. Really, it doesn't matter. 8, 9, 10, 4, 5, 6, 3, 7. There. These now are all going to disappear. How do we actually make them disappear? And this was actually an awful example. So what I should have done is something like this. I should have added a row above here. All right. So what I'll do with this row, because we actually need something to drop, I realized I should put these at the top. I'll do 7, 8, 9, 10, 11. Okay, 12. What happens now? So I need to go through this gravity thing. The way that we're going to drop these is going to be column by column. The reason we can do this, and we don't have to do them all at once, is because we're not actually going to be doing any other popping until the gravity is done. Then we're going to check if we need to do another iteration through our function to do more row and column tagging. If I look through this function, I'm going to start looking from the bottom up. If I see a single number that's, let me take a step back. The explanation I'm about to give is actually identical to the moving zeros problem. Okay, if you haven't tried that one, if you don't know it, look it up. I'll do a very brief description here, but I won't get too in depth because it is a separate problem that I consider more of a utility problem. So if you think about the moving zeros problem, in the moving zeros problem, we essentially we're given an array like 1, 0, 3, 0, 12. Okay, and then what happens is we need to move all the zeros to the end. Sorry. So we keep an index. We keep an index at the start, and then we walk through a for loop, and we tell ourselves, every time I see a non-zero, I'm going to move this index pointer up by 1, and I'm going to swap that number to my previous index pointer. Okay, the reason I'm doing that is this. This 1 swaps with itself. It kind of stays where it is. Then I look at the 0, 3, 0, 12. My index now I've moved up to here. Okay, and imagine we still have this pointer I, like in a regular for loop where we're going to be walking through one by one. This is a 0, so it's not a non-zero number, so we keep going. Our pointer is here now. Our pointer sees a non-zero number, so what it'll do is it'll say 1, 3, put it where the last index was, keep everything else as it is, 0, 12. Okay, index is moved up by 1. We see here this is a non-zero number. This right here, this is a 0 number, so we don't do anything. This is a non-zero number, so we put it where we had our last index, which is here, 12, 1, 3, 12. We still have this 0, and we still have this 12 here. We move our index up by 1. From here, since we reached the end of the array, everything from here on outwards must become a 0, right? Here we only have one item, we make this a 0. If we had any other numbers, those would also become 0, and so on and so forth. We've now shifted all the zeros to the back. That's exactly what we're going to be doing here, except I'm going to be shifting the zeros. I'm going to be shifting the non-zero numbers down, okay? Every time I see this negative, or not even every time I see a negative number, every time I see a non-negative number, or I see a positive number, because I don't want to move I guess we're going to move the zeros. Every time I see a non-negative number, I'm going to be doing this business with the index and saying, okay, let me whatever that number is, let me swap it down. I'll bring it down as far as I possibly can, maintaining the original order. And then when I get to the end and I've kind of picked all my numbers down, what I'm going to do is I'm going to fill everything else up with zeros because now we have blank spaces there. Okay? I know I rushed through that explanation just a bit, but like I said, it's a utility function that kind of comes from a whole other problem, so I didn't want to go off on too much of a tangent and explain that. Let me know if you have any questions down below. I hope that kind of made sense, and that kind of wraps up the explanation on how we're going to logically go about this. We're going to tag the rows. We're going to tag the columns. We're going to do this gravity business. We're then going to check. If we did a full walkthrough of our board and we didn't make a single change, that means we're stable. And at that point, we're done. We're just going to return the board. At any point, if we make a change, so if we check a row or a column, we're going to say, okay, we're not done. We made some changes, so we're going to have to do one more iteration after. All right, that's the high level. That's the high level of it. So let's have a look now. I was about to say let's have a seat. Let's have a look now at how we would actually go about implementing the code here. So I'm going to move this out of the way. I said we want to do three things. So actually, typically, we always like to do error check. I'll start with the error checking. Then I'll say my step 1 was crush rows, okay? Our step 2 was crush columns. And our step 3 was gravity, okay? At the end, we're going to return the board. And again, that'll kind of depend on if we're done or not. So first thing for error checking, we're just going to say if we're given some, bogus board, we're not going to, although I think we're told we're given a legit board, I'll do it anyways just for completion. We'll say if not board, just return the board as it is. Now, what I'm going to say is I'm going to have some variable called done, okay? And I'm going to presume that every time I start a function, I'm going to say that I'll assume my board is good. The reason I'm going to assume my board is fine as it is because when I jump into these items over here and I realize, oh, damn, I got to make a change, it's like, never mind, we're not done, okay? So then we're going to set it to false. So really what this means for us is we're going to return board if done is true. Otherwise, we're going to call Candy Crush again on the board. We're going to return Candy Crush of board, all right? So that's kind of our, again, just to anchor us our beginning and our end. And now this is where we're really going to jump into the meat and potatoes. We want to start tagging rows at a time, okay? So if we're going one row at a time, what we'll do is for R in range and the length of the board, and then we're going to want to go through the columns, okay? So we're going to want to say for C in range, length of board at R, except what we're going to do is this. Since we want to have remember how we want to have, we're not just going to be looking one item at a time, but 3 items at a time. If I want to have a window of 3 items, I need this thing to end a bit earlier, right? Because otherwise I'm going to go overboard. So what I'm going to do is I'm going to say we'll go until length of board minus 2. All right. So again, that's going to allow us to stop at the third last column so we can check everything that's ahead of it. Now, we are essentially going to have 3 numbers that we're going to want to compare. The first item in that row, the second item, and the third. And rather when I say row, I mean within that sliding window we have. I'm going to call those num1, num2, and num3. And the way I'm going to define them as follows is I'm just going to take the number, board of R, board of C. I'm going to take board of R and then C plus 1 because we're looking one more item over. That's the second item of that window. And then the third item of the window, we're going to want to be equal to board of R, C plus 2. Now, if you guys remember this business that I said on, first we're going to check the rows and then we're going to check the columns. Well, since we need to compare and make sure that we're looking at the same number and we might have already tagged one as being a negative, I'm just going to go ahead and take the absolute value of all these numbers to make sure that what I'm looking at is actually going to be a good comparison so that the one and the negative one will match up as being the same value. Now, I'm looking at these 3 items and I ask myself, when do I actually want to go ahead and tag these? I want to tag these if they're all the same and they're not equal to 0. So if num1 is equal to num2 and num2 is equal to num3, by logical extension, 1 has to equal 3 then. And what I'll say is, and number 1 is not equal to 0. Then what we're going to want to do is tag all these and make them negative. So not only am I going to want to tag them, I'm also going to want to say done equals false because it's like, we're not done. We're not complete. I made some changes, so we're going to need at least one more iteration to walk through and make sure that there isn't anything we got to change. The way I'm going to do that is this. I'm going to say that I want to take my board of RC and set that equal to, now, this number that we have over here, we already have its absolute value, right? So what I'm going to want to do, and I know it's equal to the absolute value of this, I'm going to want to take that number 1, right? And I'm going to want to set it to its negative value. Number 1 is always going to be an absolute value, okay? It's going to be an absolute term. I want to make sure that within the board, I'm taking that positive number and setting it to its negative, all right? I'm going to want to do the same thing here. board R C plus 1 is equal to negative num2. And finally, board of R C plus 2 is equal to negative num3. All right. What this is going to do for us, again, is essentially say, let me take whatever number I have and negate it. The reason I want to make sure that I'm negating the absolute value is because what if it was already negative, and then I negated it, I would then make it positive, and then it's not gonna crush out how we want it to. So I'm setting them to negative by making sure that I first take its absolute value and then make it negative. All right. Let me know if that makes sense. If you have any questions, again, as always, drop them in the comments down below. But that's basically the logic for crushing the rows. Crushing the columns, as you can imagine, is going to be very similar. And what I'll do there is I'll say for C in range and the length of the board at 0. So we want to go one full column at a time, okay? And then the row size that we want is going to be also in kind of in increments of 3. And we'll say then for R in range and the length of the board, it's elite speak, and the length of the board -2. Again, so we're going to want to go downwards, but only up to the third last item, because we're going to want this sliding window of size 3 perpetually going downwards. And we're going to do something similar. We're going to say number 1 is equal to the absolute of all these, and maybe I'll even get smart here and just copy paste it. Except we're going to change one thing. Since we're going downwards, this is going to be R plus 1, and this is going to be R plus 2, because we want to look at the items that are 1 and 2 items below where I am, not to the left or right. Then my condition here stays the same, and actually the rest of this is pretty much all the same. Again, barring this fact over here, this is going to become R plus 1 and R plus 2 because I'm looking downwards, not to the left or to the right. And so, unless I've made any glaringly obvious mistakes, which I don't see right off the bat, but I wouldn't put it past me, this is actually the logic for tagging the items that we want to be crushed upon, like when we actually do our gravity. And we're going to implement that gravity step right now. Now, for the gravity step, we're going to want to go, let's think about this. We're going to want to go column by column, right? So logically then what we do is we'd say C in range, length of board 0, kind of like what we were doing here. And then what we'd say is the following, is we want to do two things. One is we want to say move all positive numbers down, so the actual cells we have, the legit ones. And on top of that, what we want to do is we want to say put zeros in for missing pieces, right? So we're gonna have to replace those. The stuff we move down, we're gonna have to replace with zeros, and everything that's kind of come down. So in order to move those down, this is like what I was talking about, the moving zeros piece. I'm gonna start with we're gonna go one row at a time, and we're gonna go. Let me think about this. If we want to crush one at a time, so if you think about how we had that array and we went from left to right, imagine tilting it now column-wise, and we want to go bottom up, right? So what I'll do is I'll say for R in range and the length of the board -1, so we want to be at the bottom, and we're going to go up by 1 unit at a time until we get to 0. Well, first things first. Actually, let me move this. Yeah, actually that's fine. I'm going to want to create that index that I was talking about. So index, I'm going to set that equal to length of board -1, meaning that's going to be the first place where I'm going to replace, sorry, that's a really weird angle, I just realized, where I'm going to replace my numbers with that as we're dropping them down. And that's where I'm going to bring my greater than 0 numbers to my actual cells. So what we're going to do is as follows. We're going to say if board of RC is greater than 0, what's going to happen is this. I'm going to set board of index C equal to board of RC. So I'm effectively moving that number down, and then I'm going to set index minus equals 1. So that means that I'm going to move my index 1 upwards and saying everything from, everything below me needs to stay. From here on up, if you don't move anything else down, the rest of this needs to become 0 because it's like everything else is dropped. All right. Once we do that, I'm sorry, I tried to brain fart. Once we essentially do that, so that'll actually bring everything down to where we want it to be. Once that's done, we've got to fill in zeros for essentially all the missing pieces or for every item we brought down that's now still duplicated. Again, think about the moving arrays, moving zeros to end of array problem. We're gonna fill all those in with zeros. So we'll do another for loop, and we'll start this one from where the index last was, and we're gonna make it until -1, and we're going kind of down by 1 unit at a time. Like visually, we're going upwards, but the row index is gonna be decreasing. And so what we'll do is we'll say forward of r of c is equal to 0 there. And in fact, again, now if I haven't made any glaringly obvious mistakes, we're actually done. That gravity function is the one that will bring all the items down. And like we said, if we've at any point made a change to our rows or columns by tagging them, done will be false, as in we are not done. So when we get down here, we'll return the board if we're done. Otherwise, we call this thing again, and I think this should be self dot. It might yell at me if I don't do self. Otherwise, we're not, then we got to do it again. In this next rendition, I start by saying done is true. If I don't crush a single row, if I don't tag one, that is, if I don't tag a single column, done will be true. So we're not going to have to do any of this. And maybe, you know, I guess if I think about it, maybe we can just do this if done is true. So maybe I'll say if done, we can actually just skip this. This won't really save us on asymptotic time analysis, but in real time, it might do something for us. So I'm going to move myself up over here and try to run this code and see if I somehow got it miraculously on the first try, which I didn't. It looks like I'm about to time out, so there's something that I missed here. Let me see if I can find the error. And I'm sorry, guys, I just caught it. It's been a long day. This is not true. Like this if statement I just threw in here for fun and sprinkled like confetti. Like, do not do that. So the reason this never actually happened is because that means that, you know, if we never set done to true, like we're not actually going to end up in this loop. We're never going to crush anything, because we want to be crushing this if it's not done, right? So that means if we tagged anything, then we want to jump into there. So I think if I run this now, it should be good. There we go. I was saying like the opposite. I was doing the opposite of what I meant to do. So I'm sorry about that. I hope that didn't cause too much confusion. The problem is solved. I know this was a bit of a longer video. I do apologize. Thank you for those of you who have stuck around. I hope it was worth it. This one took like, it's a bit of heavy lifting to get this done. Oh, I'm sorry, I don't know what this tag is. There we go. I know it's a bit of heavy lifting to get this one done. It's not the easiest problem in the world. It's involved, but I think it's an interesting one nonetheless. And so let me know down below if you guys liked it, if you like this longer style video. And as always, like, comment, share, all that stuff. I'm getting hungry. I haven't eaten dinner yet, and it's getting late. So I'm out of here. I'll see you guys next time. And yep, study hard. Peace.